Today I'm talking about medical cohort analytics, which was my research topic during my postdoc in a slide with Sihem. I'll have a quick discussion of my background and then we'll delve into the subject. So I performed research on data exploration, which means enabling analysts, data scientists, information consumers, domain experts, any kind of connoisseur to interact with their data, which means to consider them inside the loop of data analytics and incorporate their feedback in the decision-making process. Data exploration is indispensable today because our datasets are voluminous. Organizations collect large and complex datasets to have more affluent insights, and this needs to develop data exploration tools to determine whether the analyst should go. Data exploration emanates from EDA, exploratory data analysis, introduced by John Tukey in 1977, which is a known field in statistics in contrast with initial data analysis, which proposes to look beyond simplistic statistical values of average and standard deviation. Today, with the advent of more computational powers and more available servers, EDA is upgraded to data exploration, either with efficiency techniques in databases or interaction and presentation methods in HCI and visual analytics. Since 2014, that I started my master internship followed by my PhD with CM, I've explored data exploration in myriad ways. During my PhD, I focused on exploring user data and contributed to mining, exploring, recommending, and visualizing user groups. Then I had a postdoc of 2 months with Marie-Christine, where I investigated on exploring ontologies and RDF tuples for the application of students' progression in French medical education systems. Then I moved to the Ohio State University in Arnab Nandi's team and worked on exploring spatiotemporal data such as aviation data, car rental, and bike sharing data. Then I moved back to France and commenced a postdoc with Sihem, this time on exploring medical data, which is the topic of today's presentation. I'll then join Naver Labs Europe as a research scientist, where my immediate project will be on exploring POI recommendations for ephemeral groups. Let's come back to our subject, which is medical cohort analysis. I would like to start with the big picture of medical data analysis. I believe that the research around medical data analysis can be summarized in 2 keywords: public health analysis and precision medicine, which encapsulate the past and current status of the research directions, respectively. What are these 2 keywords, and where do we position? 10 to 20 years ago, even now, we hear discoveries like effect of radiation for breast cancer, influence of air pollution on dementia, or Google's private company Coleco researching on factors for immortality. The common denominator among all these discoveries is that they are health-related conclusions about the mass of population, not the specific people, not the specific groups. We call it public health analysis, which are recommendations which can be used more or less by anyone. Now, with the growth of the computation edifice, public health analysis is ossified, and we consider precision medicine as a trademark of nobility, which calls for a new medical model which is tailored for individual patients. Now, your Apple Watch or your Fitbit wrist can signal you on the anomaly of your heart rate by analyzing your historical data. A health app on your smartphone can signal you on eating too much sugar today based on your history and your specific characteristics, such as suffering from diabetes. These are all examples of precision medicine, which are customized recommendations for individuals. If we consider public health analysis and precision medicine as 2 extremes, one with no customization at all, for example, how does air pollution affect people in general? And the other one with full customization in the level of individuals, for example, how does air pollution affect Julia's health? We are interested to meet both halfway, which is to consider a specific set of patients, which we call a cohort. For instance, we're interested in a question like, how does air pollution affect the health status of middle-aged females in Paris suffering from sleep apnea? See that the cohort is now specified by the analyst with some predicates of her interest, for example, being female or being in Paris. This was our focus in this project, which is a part of a bigger edX project called LIFE. But why do we need to focus on cohorts? What do we gain from that? Let's see that in an example. We consider Julia, who is suffering from epilepsy or any other chronic disease, and is trying to understand what has caused an increase in the frequency of her absent seizures or any other symptom. Public health analysis is imprecise for her case, and she needs something more personal. Precision medicine may be able to provide a very specific recommendation about her only if enough data is available, which is not often the case. And moreover, she gets very narrow minded insights. We propose to look at the cohort that Julia is a member of, which is the cohort of patients suffering from epilepsy. We can benefit from this coterie at least in two ways, which we call internal and external benefits. The internal benefit is for each member of the cohort, including Julia, where she observes the profiles of lookalike patients and sees where she falls relative to the norm. Moreover, external benefits also exist for actors outside the cohort, for example, for medical units, to prepare special care for the specific needs of the cohort members. Now, what does analyzing cohorts mean? It's an approach for medical experts to comprehend how the health of a set of patients is affected by treatments and diseases. In our interactions with our medical partners, we fathomed that they often ask one of the following questions for analyzing their cohorts under investigation. What has happened to the cohort? What happened to similar cohorts? And what will happen next? The very first question relates to representation of the cohort, to observe how the health status of the cohort members have evolved. For instance, for the cohort of middle-aged females in Paris suffering from sleep apnea, the expert wants to know what treatments and diseases led them to sleep apnea. The second question relates to exploration, to observe similar cohorts and get inspired from how their treatments and diseases have evolved. For our example cohort of middle-aged females in Paris suffering from sleep apnea, we can explore and observe the cohort of young females in Paris suffering from the same disease, or middle-aged males in Paris suffering from the same disease. Also, the last question is on the prophecy of future risks and prognosis. This last question has been covered in the state of the art more prominently than two other questions. Our focus today is on the first two questions, how to represent and explore cohorts. So let's see what's the intuition behind representation and exploration. Cohort representation is a recourse for medical experts to understand which sequence of treatments and diseases lead to a final health status. For a cohort under investigation, experts can benefit from a representation to get answers for questions such as which sequence of treatments is the most relevant to death, or which treatment is administered right after admission which kept cohort members alive for a longer period, or what changes in body mass index led to death. On the other hand, cohort exploration enables navigation in the space of cohorts to compare their health evolution. For instance, for the cohort of patients inside Grenoble suffering from sleep apnea, one can explore to the cohort of patients outside Grenoble suffering from the same disease, where the comparison reveals insight about the difference in health evolution and probably the effect of air purity on their health. That being said, this is the outline that I'm going to cover in the rest of the talk. First, I describe the structure behind healthcare data. Then I discuss technicalities behind cohort representation and exploration. And I finally discuss experiments. And with this, I conclude. So, about the data. We used two real healthcare datasets. One called Agir, originated from a company around Grenoble for providing medical assistive machines to patients with respiratory problems. The other one called Rambam, a public dataset coming from a hospital in Haifa, Israel, with the same name. The latter has more patients but less actions. Actions in Agir are treatment and health markers. In Rambam, it's visited departments and wards in a hospital. Also note that Agir has more recency than the other. In general, healthcare datasets have a star schema where patients are at the center and their associated events around. Here is the Agir dataset with hospitalization records, BMI markers, and others. To flatten this data and simplify the structure, we denote everything associated to patients as events, where an event is a tuple of the form patient, action, and a timestamp. For instance, John being under oxygenotherapy in May 2019 is an event in Agir dataset. Or Mary visiting the hematology department at March 2018 is another event in Rambam dataset. Then we denote the history of each patient as patient trajectory. A patient trajectory is a list of temporally sorted events for the patient. Here each circle represents an event with a timestamp and an action for that patient. It all starts at time t0, which is the admission time, the first time that the patient is seen in the dataset. Then later we observe that this patient has been hospitalized for 2 months after admission and has stayed in the hospital for a full year, as 12 months after that the hospitalization ends. Now we can define a cohort, which is basically a set of patients and their trajectories, where those patients are defined with a set of predicates. Here is an example of a cohort defined by predicates like middle-aged, female, living in Paris, and suffering from sleep apnea. It returns 3 following patients with their trajectories. See, when there is more than a trajectory in a cohort, there is heterogeneity. This is a takeaway from this slide, that events happening in different times and of different types in different trajectories. This makes digesting a cohort in its current form tedious, and we'll later see what should be done for that. With these definitions of events, trajectories, and cohorts, now let's focus on cohort representation. Recall that the aim in cohort representation is to help medical experts understand the sequence of treatments and diseases for patients over time. I mentioned briefly before that the challenge for representing a cohort is heterogeneity. Cohorts often consist of hundreds of patients with various types of events. Imagine, for instance, a cohort with 500 patients. Looking at all varieties of event types in different times is indeed a burden on the analyst. Based on our exchanges with our medical partners, we realized that an ideal way to represent a cohort is a single end-to-end story which is succinct and readable. For instance, in response to the question of the expert, what has happened to the cohort of middle-aged females in Paris with bronchitis who stay alive, the cohort representation system should be able to recount a succinct story such as the cohort starts with oxygen therapy, follows ventilation after 11 months, and takes another ventilation treatment 1 month later. How can we find such an ideal representation? Let's simplify our problem and imagine that our cohort contains only 2 patients. How to convey a single end-to-end story for these 2 patients? There are at least 3 different ways to do so. One is to forget about order and the time of the events and translate patient trajectories to bags of events. In this case, the common representation for patient 1 and patient 2 will be the set A and C, because these 2 events exist in both trajectories. We may incorporate order and represent the cohort as a sequence of A, then C, then C. This sequence can be played on both trajectories and is a valid representation. Sequence mining algorithms are capable of generating such representations. We can go even one step further and incorporate both order and time by associating probabilities to the sequences. Here, we say although A's here are common between the 2 patients, but they haven't occurred at the exact same time and they are swerved a bit. So there's a penalty associated to this case, which represented with 0.7 probability. However, for the case of C, it happens exactly at the same time in both trajectories, and hence we associate 1 to it. We opt to offer a time-based representation of cohorts which contains both order of events and their timestamps. To understand how time-based representations work, we define an additional notion, which is an aggregated event. Coming back to our data model, it extends the notion of events, where an aggregated event is a tuple with several patients, a single action, and several timestamps. Coming back to our example, here is an aggregated event containing patients 1 and 2, the action A, and the timestamps T5 and T7. But should we incorporate all possible aggregated events in the cohort representation? Recall we need a succinct and readable representation, hence it's absurd to consider them all. Hence, we need a yardstick to measure the quality of aggregated events. These measures are dispersion and significance. Intuitively, an aggregated event is dispersed if its timestamps are spread in time. Also, an aggregated event is more significant if it contains several different timestamps. Here is an example. There are 2 aggregated events. E1 bar for a set of patients P on action X in timestamps T0 and T6, and E2 bar is for another set of patients P prime on the same action in timestamps T1, T1, T3, and T4. We define dispersion as the difference between the largest and the smallest timestamps, here 6 and there 3. And we define significance as the count of timestamps, here 2 and for the other one 4. Then E1 bar is more dispersed but less significant. With these yardsticks, we can now formally define the problem of cohort representation. Given a cohort C and a significance threshold sigma, the problem of cohort representation is to find all aggregated events E bar of C, where for each E bar in E bar of C, two following conditions are satisfied. First, the significance of each E bar is larger than or equal to sigma, and the dispersion of each E bar is minimized. We've proved that the problem is NP complete by a reduction from multiple sequence alignment problem. Here is our methodology for cohort representation. It starts with the medical expert who specifies the cohort, here old Grenoble females who are alive, which selects patients P1 to P3. Their trajectories are retrieved, and then we obtain aggregated events between each pair of trajectories. Then we compute the significance score for each aggregated event, and using a significance threshold sigma, we prune them. For instance, here with sigma equal to 0.8, the representation is A at T0 and B at T5. With sigma equal to 0.3, the representation is A at T0, B at T5, and C at T11. This life cycle shows how the significance threshold is satisfied, but not how the dispersion is minimized. The technique that we use to populate aggregated events is sequence matching, which only delivers once with minimal dispersion. Sequence matching is initially proposed to find matches between protein sequences and discover homologous protein pairs. We revived the method, more specifically the Needleman-Wunsch algorithm, to find the aggregated events with minimal dispersion. To do that, we first build a Manhattan graph using cost tables. In biology, cost tables show how far two genes are from each other. In lack of such background knowledge in our case, we use generic schemes and consider +1 for a match, -1 for a mismatch, and -2 for a gap. We fill the table and we backchain to obtain an alignment between two sequences, which denote the aggregated events with minimal dispersion. Here in this case, for instance, the aggregated events will be on actions A and C. A cohort is built with high significance and minimal dispersion. But how can it be useful? From a systematic perspective, this representation enables storytelling for the cohort. Starting with event A, the cohort follows up with B after 5 months and then C after 6 months. This can help in various ways. For instance, to decrease hospitalization cost in the first 5-month period of the treatment, or to prepare the medical unit relative to events A, B, and C and not other events, or organize care subscriptions in periods of 5 to 6 months. The last point about the representation is that how efficient the approach is. So the worst case complexity of cohort representation depends on the size of the cohort and the length of the trajectory. So obviously, to improve the efficiency of cohort representation, we need to reduce either the lengths of trajectories or the number of trajectory comparisons. In order to reduce the trajectory length, what we find out is that we can filter out unnecessary comparisons in the Manhattan graph. In case we don't have any cost table, comparing events of different actions doesn't make sense, so we can easily filter them out. And in case of reduction of trajectory comparisons, we have two opportunities: trajectory families and stratified sampling. For trajectory families, what we do is to generate non-overlapping clusters of trajectories in a time-agnostic way. We employ K-methods as the clustering approach to obtain K-families. We then abstract patient trajectories with the method of their family. So for example, to compare the trajectory of patient 9 with the trajectory of patient 2, what we do, we only consider their methods. So we only compare the trajectory of patient P5 and the patient P3. Also, if you want to compare the trajectory of patient 1 with the trajectory of patient 6, we also compare the same methods, P5 and P3. So it reduces the number of comparisons. Also, in terms of stratified sampling, what we do is to generate a sampled cohort, which is the subset of the original cohort, by picking at random some members from each demographic group of a given stratification attribute. A demographic group is identified with an attribute value pair. For example, if the stratification attribute is gender, gender female and gender male are two demographic groups. Stratified sampling ensures that the sampled cohort members represent all demographic groups. The sampling ratio R that we use to obtain samples is a value between 0 and 1, where values closer to 0 lead to more reduction. Now let's jump to the second contribution, which is cohort exploration. Hitherto, we discussed about the internal dynamics of a cohort, how to represent members inside the cohort. Once the expert investigates the representation of the cohort, her next natural request is to explore similar cohorts. How do we select a candidate cohort for exploration? Or better to ask, how do we compare a pair of cohorts to examine whether they are relevant or not? First, we compare them in terms of similarity. The similarity between two cohorts C1 and C2 is the similarity between their representations. However, cohorts may be similar but also highly overlapping with redundant patients, resulting in no novelty. We also need to measure how well they are separated from each other. In other words, cohort exploration should return a limited number of well-separated similar cohorts to help experts explore different directions in their healthcare data. Given a set of cohorts C, where the size of the cohort is less than or equal to omega, we measure the amount of information that C conveys using its channel's information entropy. In the typical graph-adapted definition of entropy, pi of Ci and Cj is the amount of patient overlap between cohorts Ci and Cj. With the measures of similarity and entropy, we can now define the problem of cohort exploration. Given a cohort C, a similarity threshold theta, and a size threshold omega, the problem is to return at most omega cohorts C1 to C omega, where similarity of each of these omega cohorts with the input cohort C is larger than or equal to theta, and the entropy of C is maximized. We've proved that the problem is NP-complete by reduction from maximum sub-edge graph problem. Our solution for cohort exploration involves three different stages. First, we limit the set of candidates to contrast cohorts and sort them in increasing order of preferability. Then, we compute the similarity of each identified contrast cohort to the given cohort. And then, we return omega similar cohorts with maximized entropy. But what are contrast cohorts? Contrast cohorts function as our candidates for exploration. We define a mu contrast cohort as the one which differs in at most mu attribute values or actions. For instance, for the cohort of females in Paris, males in Paris is a contrast cohort with mu equal to 1. Mu contrast cohorts are exploration candidates as they are similar to the input cohort but also different enough to provide additional insights. This formula shows how we obtain the set of contrast cohorts for the input cohort C. So, having contrast cohorts, how do we maximize entropy? The general scheme is simple. Why we don't have yet omega cohorts, we continue and get the best next representative cohort to be included in the set of exploration cohorts. This greedy process can be optimal if there is a total order between exploration candidates. This is why we use peripherality function, which is a common centrality measure in social network analysis. The intuition behind this measure is that the more peripheral cohorts, which are farther from other cohorts, contribute more to entropy. The last thing about cohort exploration is how efficient cohort exploration is. We observed that the bottleneck in cohort exploration is similarity computations between cohorts. So we surmised that by avoiding similarity computation for irrelevant contrast cohorts, the execution time improved drastically. Inspired from double dictionary encoding, we build an event set for each contrast cohort regardless of the time of occurrence. Event sets then enable early pruning of irrelevant cohorts. Simply, if there is no intersection between the event sets of two cohorts, we don't bother to compute the similarity between these two cohorts, and this contributes to efficiency. And now we show a few experiments about the efficiency and effectiveness of our medical cohort analysis approach for representing and exploring cohorts. First, we discussed the performance of cohort representation using trajectory families and stratified sampling. The above figure shows the execution time of cohort representation with different trajectory families, 10, 50, 100, and 200 trajectory families from left to right. A general observation here is that even representing a giant cohort with 20,000 members is feasible with trajectory families within flow preserving latency, which is 1 second. In case of a GEAR dataset, which is what the results are showing, the execution time does not exceed 100 milliseconds, 160 milliseconds, and 640 milliseconds when 10, 50, and 100 trajectory families are applied, respectively. Also, in case of stratified sampling, what we show here is the execution time with sampling ratios of 0.2, 0.4, 0.6, and 0.8, respectively from left to right. In Azure dataset, when the age attribute is used for stratification, the execution time is drastically reduced compared to random sampling. The reason is that the GEAR contains patients with respiratory diseases, and the patient age is often a good indicator of the respiratory disease. Hence, the age stratification makes homogeneous samples where trajectory comparisons can be done more efficiently. In both datasets, gender is the worst stratification attribute, as the same health situation may happen for both genders. Now we focus on the quality of representations. We borrow 3 quality measures from the domain of process discovery, which is fitness, replayability, and specificity. Fitness verifies if trajectories of cohort members have at least one footprint, which is like a common action in the representation. Replayability is a stricter measure and verifies if all actions in the trajectories of cohort members are observed in the representation, which means that the trajectories can be replayed on the representation. Also, specificity verifies how specific the representation is to the cohort members. They all return a value between 0 and 1, where values closer to 1 indicate a better representation. We observe that fitness increases for larger cohorts and for smaller significance thresholds. Increasing the size of the cohort or decreasing the significance threshold lead to cohort representations with potentially more distinct actions, hence increasing the chance that each member finds a commonality with their representation. The same interpretation holds for replayability. Note, however, that the strict nature of this measure leads to lower quality values compared to fitness, where all values are lower than 0.5. For specificity, the influence of the cohort size is not evident, but the significance threshold has the same effect as 2 other measures. This means that the cohort representation with a high significance threshold is less specific to the cohort under investigation and can also be replayed by patient trajectories outside the cohort. Now we also focus on the performance of cohort exploration. The figure on the left shows the influence of mu. The one in the middle shows the influence of the number of exploration options, which is omega, and the one on the right shows the influence of similarity threshold, which is theta. In case of mu, the execution time reflects the growth of mu, where it exceeds the flow-preserving latencies with mu larger than 2. In case of omega, we observed a slight increase in the execution time for more exploration options. The execution time is below the flow-preserving latency even for the case of 100 exploration options. Also, in case of the similarity threshold, we observed that increasing the similarity threshold makes the candidate cohort selection process more restrictive, hence fewer candidates cohorts will be generated. Then the execution time reflects this observation, and it shows that it is below the continuity preserving latency, which is 100 milliseconds in case mu equal to 0.8. Event sets contribute to the execution time, but the influence is less visible with higher similarity thresholds. The reason is that higher similar cohorts have many potential actions in common, hence fewer prunings are possible with event sets. So to conclude, I discussed a data-driven framework for medical cohort representation and exploration. Representation is about building a concise representation of a cohort by pruning insignificant events. Exploration relies on finding contrast cohort as exploration candidates by maximizing entropy. For an efficient computation of cohort representation, we employ trajectory families and stratified sampling. and for cohort exploration, we employed event sets. Our next immediate action is to deploy a distributed infrastructure where different components of representation and exploration can be performed in parallel.